So after we covered the basics in transportation yesterday, and we learned all the building blocks for intelligent transportation systems, today we're going to see actual examples. You're going to be doing what engineers do, using traffic simulators for modeling, for changing traffic control parameters in different ways within your transportation network, and seeing how those changes would change your network. Let me give you this small example first. The instructor that taught me this course a while back told us about this. A few years ago, this was a project being done with the Ministry of Transportation in Ontario. They were trying to understand, I think also it was with the City of Toronto, they were trying to understand what the effect would be of having a separate lane for the streetcar on Lakeshore. So apparently previously it wasn't separate. They were trying to study if you have a streetcar sharing the road, if you have a road which is being shared by vehicles and a streetcar such as what you have on College Street, and if you have a separate streetcar, what would change? So a streetcar having its own lane, what would change? What would change for the streetcar? What would change for the vehicles? Yes. The streetcar's motion would not be affected by the cars. The streetcar now has a dedicated street, basically dedicated lane, and it doesn't have to honk the horn for vehicles to actually move or not stop where they're not supposed to. What about the vehicles then? What's happening with the vehicles? Yeah. It limits their space. The capacity that you have for the vehicles is actually less, right? So if you had 3 lanes, now you have 2 lanes. That is taking into account that the streetcar was sharing the road with the vehicles. So you have this problem, and this problem comes to an engineering firm or a consulting firm, and they need to figure out what's going to be the effect if we have that dedicated lane for the streetcar. How are things going to be different for the vehicles? Where is this effect going to go to? So they modeled this in Paramics. They have already, from the road sensors, they have come up with the source destination pairs, or the OD matrix, that defines how things are going, where people want to go. And then they have the model, they change something in the middle, which is they make the streetcar lane separate. Then what they're studying is how the vehicles are going to shift where they're going, because now the capacity is smaller there, right? It's going to get congested, so they're going to shift to other places. They're going to shift. They can't shift to the lake because that's what you have south, so they're going to go upwards. So they studied the effect going all the way up to Dundas Street, which is more than 3-4 streets north. They realized that after Dundas, it's not going to be affected. So they measured whether they're going to use congestion in other streets. And after they come up with the results with the study, they realized that it will work, and they then provided the results to the ministry, which implemented it. A similar type of project was for the St. Clair streetcar, which is also separate. So throughout your activities now, if you have any questions regarding how what you're doing is used, how people do it, and how people do more difficult stuff also in the industry, please feel free to ask me. Okay, so I have just a few slides at the beginning. So why are we doing traffic flow analysis? Why are we using simulation models? Well, it's hard to do tests with actual cars because you need to have your own cars. Every time you're going to do a test, you're not going to get rent 2,000 cars and then do testing with them, right? So in different fields, you use test beds, like actual devices, which would be like computers, for example, in networking. But in here, you can't actually get that many vehicles. and you need your simulation, you need the results to be accurate, and for them to be accurate, it has to be large scale. It has to be representative of what you actually have in the road. So you start with the traffic flow model, how vehicles are moving, the network routing model, what you have in your network, your roads and your links. And so what you're ending up with is a physical replica of what you have, or in other terms, it's a mathematical model. You can think of it in that way. That's why you have those equations of how the vehicles are moving and how aggressive vehicles are changing lanes, so on and so forth. And how do you do? Why do you do this for? You do this for planning and policy analysis, and to design new infrastructure, control systems, information systems, and also managing the operations in your network to figure out what you need to change in the intersections, which you're going to do tomorrow. Network operations and performance, so freeways, streets, corridors, and whole networks. You're doing things like this in the afternoon, and your other systems. Okay. So having the accurate models in a simulator, you can answer your what-if questions easily. Then you could say, what if I build another highway here? What would be the effect? Then you do the study. Then you see the difference. Then you measure the cost. OK, I'm paying this much, but my gain is this much. Is it worth it? If you don't have the good tools, you can't do the analysis correctly, and you'll end up building a highway that you'll have to then close, as we found out yesterday. So this is what we mentioned yesterday regarding macroscopic models. And then you start thinking about the fact that cars don't actually flow like water, right? Water flows smoothly. I mean, if you look at a river, it kind of moves slowly, unless you have big trees in it that are moving a bit slowly, right? I'm remembering what you were mentioning yesterday, where you have vehicles that are going slowly and vehicles that are going faster, and you have stop and go. But it doesn't actually flow like water, right? So if you zoom out and you look at it from a distance, it does look like water. But if you zoom in, there is the small interactions between the vehicles. That's where microscopic models come in. Okay? Microscopic models define how every single vehicle moves. And that's what you're seeing in Paramics. That's a microscopic model. Okay? So in here, the tasks that you have as a driver include car following. So you're in a lane. There's a vehicle in front of you. If the vehicle is going, it's less than the free flow speed or the maximum speed, you'll be following the car in front of you. If the vehicle in front of you slows down, you have to slow down because you don't want to crash. The other thing that you have to that is modeled is lane changing models. So what's the distance that needs to be ahead of you or behind you for you to change a lane? All of those things depend on how aggressive the driver is. And the other thing, what I mean by that is an aggressive driver would change a lane with a smaller distance ahead of him and behind him. And the other one is routing through the network. So how do I choose my route? How do I choose where to go based on what I'm seeing around me, as we saw yesterday with user equilibrium and possibly with navigation systems coming into play. So car following models, what they do is they bridge the gap between microscopic and macroscopic. They make things smoother so that you see a stream of vehicles, as you can see here. And then you can start basically joining the two, and then from micro to macro. And when things settle down, so under steady state, micro and macro have lots of things which are similar. That's why you can model that. So you apply the steady state condition, which is if you have a group of vehicles together, the speed of one vehicle in that platoon is the speed of the platoon itself, right? So if you do that and you solve for the boundary conditions between different boundaries, you'll get good results for your flow and your density. Okay, so this is the picture of Paramics here. So just to sum up, in terms of microscopic versus macroscopic, one of the things that you can do is, so for micro, you have the discrete in terms of the flow. So you have to do it every second, let's say, or every half second. So as we were mentioning yesterday when we divided the road, a vehicle is here after half a second. Does it cross or does it stay where it is? That's how you can build it. You cannot build a continuous one because a continuous one is like water. While for the macro one, you can have both. You can have the discrete, which is divided into instances, and the continuous one. And one of the things which is a bit different here is meso. So if you have a discrete one on micro, this is something in between micro and macro. So if you are trying to do huge studies with hundreds of thousands of vehicles, or actually even millions, then you can't use micro. Because micro, you'll be modeling every single element. It would be too accurate, but it would take so much time to actually come up with any result. One example of what Hussam Abdelgawad, the person who I've taken these slides from, is a postdoc in the ITS group. What he has done in his PhD thesis is he has developed an emergency evacuation plan for the city of Toronto. He has won an award for this, and the city of Toronto has actually accepted, and the city of Toronto's plan of evacuation is his plan of evacuation now. So to be able to do something like that, he had started with micro, but then he shifted into another type of simulator where you can do things in far bigger, where smaller things are micro, but a lot of the relationships are macro, because there you can do things faster. Yes? Yes. Yes. So the results of the thesis were something around this. You can look it up online, actually. It's available. If you put T-space U Toronto and this name, you'll find it. But if you don't do anything, it takes something like 24 hours for everyone to leave. The average is maybe 6 hours for everyone to evacuate city of Toronto. And there are people that haven't left up to maybe 24 hours, because if you don't have an organized way of leaving, of leaving or evacuating, there's chaos, basically. People will be blocking their own ways. But if you are communicating with people, as we mentioned yesterday, right? So you're designing an optimal way of guidance for vehicles and for users. The average goes down to 3 to 4 hours, and the last person that, or maybe 2 hours, I can't remember the exact details now, and the last person that goes out within like 4 hours or 6 hours. Yeah, it makes a big difference, but in order to come up with studies like that, and the city of Toronto, for it to accept it, it has to be really, really accurate. And there was an equation here. If you can actually see the thesis, the whole thesis, and there are papers about it. I had them yesterday. So some of the formulas that you have like triple summations, and look, 4 of those. So you have a huge space on which you're trying to optimize. So lots of possibilities, and things need to be done faster. Okay. What would be the differences? You have difference in terms of computation time. So macro is faster because you're not modeling every single vehicle. The required resolution that you need. So depending on what you are looking for, you might be using macro or micro. If you just care about what's happening overall, you can just use macro. If you care about every single vehicle and how some vehicles are being affected, you need to use micro. So potential accuracy versus validation efforts. So accuracy, of course, it's better. The accuracy is better with micro, but the effort it's going to take is going to be more, and the waiting time for the results, and also for routing models. Okay, so this is what you're going to do now. I'm going to open Paramics. now you're going to go through the first-time user's guide systematically. I want you to be able to learn the different functionalities and what you can use. Please do not skip any steps here. So you have all these different steps within the first-time user's guide. Please do them. The activities after that, I won't guide you where you need to go to change a particular thing. You have to figure it out because you're learning it now. So please do not skip any steps. Later on, if you need to, let's say, change a demand, you need to know how you're going to do it, or you need to add a lane. You need to know how you need to do it. So first, you're starting with this. And then the activity after that, you're going to build a four-way intersection. In the afternoon, when you come back at 1, please do come back at 1. Please don't be late in the afternoon. We're going to a tour of the ITS lab, and then there's a guest presentation there. And then we're coming back to 2 more activities using Paramics, seeing different ITS solutions, basically, within Paramics. OK, do you have any questions? OK, so please stay in the groups that you are in. Regarding the usage, whoever is sitting there, please work as a group. And then what I would suggest is every maybe 15, 30 minutes, you can switch. Other people could actually sit so that they could interact with the simulator in a different way, but also contribute. And the more you learn together as a group, the faster you'll be able to do some of the activities later.
Oh, it's my hotspot.
Oh,
it's my hotspot. So each hotspot has 10. There should only be 10.
I saw what you did there. Here. Oh, wait, what just happened?
Kill people.
So whenever there's 10 cars, they'll just destroy something.
Yeah. I think it just limits the amount.
And alright, let's just. Alright, so we do the next step. Sure. Alright. I'm good. Oh no, I mean on this.
See how it is.
Yeah, let's actually follow the next step. Vehicle dynamic. Oh, you can get different cars.
We're not going to make them all Lamborghinis. It's unrealistic.
You're right. Make them all mini buses.
Okay. Oh wait, why mini? Just go straight to bus.
Unfamiliar, right? Our drivers aren't familiar. No, that's a bad option.
No, make them unfamiliar. Like apparently they take longer routes.
Wrong lane.
Yeah, and they'll sometimes go into wrong lanes.
So
They'll be in the wrong turning lane, so they'll be on the middle lane if they want to turn right, so they'll go through the second lane.
It's like a one-way road, but they're going the opposite direction.
Yeah, some like that. Is there a one-way road? No, I don't think we have one-way roads. So.
Oh, look in this stadium.
No, I mean in this simulation.
No, there is. It's right here.
There aren't Toronto.
Is there cars? No, man.
Oh,
There are quite a few in Montreal.
There's a crash somewhere.
Seriously?
Yeah.
Go fix it. See, it's because you made them unfamiliar. Okay, too much animation.
What's that falling?
What did you make the fall?
Which type for dump to the most efficient way. This one. This one?
No. But there's a couple. You just lost it. Yeah.
Let's look at the video. Just watch the video.
What video?
The vehicle dynamics video.
Where is it? No, that's the audio demand. We're trying to figure out stuff.
So now when you press it, you'll see the speed changing. You can press space instead of object. Okay, now if you try to capture one noise, for example, going towards a light, then you'll see it slowing down and then speeding.
I think that was a good speed before. Yeah. That's how you yeah, that's quite realistic. It's slightly fast actually, but it's slightly fast. But it's too.
Wait, what? Oh, because it left the city.
Oh, look at that.
Oh, awesome.
Look, they all pile up at one area.
Yeah, because it's a stoplight.
It should be like.
We should take them when they
You know,
just.
like I know. Here's a random theory I thought of. Like all lights should be like aligned in a way when they're on.
No.
Okay.
And higher speed limits. And then, but then that will lead to like higher amperage. Like, long amperage.
더 크게 만들고 싶겠는데. 이 강 있는 데까지 다. 지도 딱 있으면 거기에 맞춰서 딱 그려져.
I'm pretty sure there's supposed to be some data here, but it's not getting it. It's weird. So let's go to the next thing.
컨젝션 많은 것 같아, 그렇지 않냐? 그거 한번 띄워봐, 컨젝션 하는 거. 왜? 그거 했잖아. 그걸 이용해서 차와 부딪힐 수 있지 않을까? 차와 차를 부딪히게 할 수 있지 않을까?
And then it'll be sign off like that. You know, I mean like. See, I want to see how it looks. But it's anyways. Yeah, bro. So you have like a troll face.
Here, can you put the 3D here?
Don't try that. We don't know. Just zooming in.
Oh, yeah, we can zoom.
Oh, so this is the building in the middle of
Oh, dang.
Did I crush a bus?